we have looked at finding shortest paths or finding optimal solutions, and we looked at branch and bound, which was a blind or uninformed algorithm, in the sense that while it did guarantee that you will find the shortest path or the optimal solution, it had no sense of direction, that it could go off in any direction. This brings us to probably the most well known algorithm that you are going to study in this course, which is algorithm A star, which combines the properties of the algorithms that we have seen earlier. A star was given by Hart and Nilsson and Raphael in 1968. So, it is quite an old algorithm. They were at that time Stanford Research Institute, which is now called SRI International. It can be seen as an extension of Dijkstra's 1959 algorithm for shortest path, all paired shortest path as it is called. A star achieves better performance by using heuristics, which is what we will borrow from best first search essentially. And of course, Dijkstra's algorithm was not concerned with reaching one particular goal state. It said that find shortest paths to all the nodes, and therefore, it did not need a sense of direction. But our task is to say that you are given in a start state and you want to go to a goal state, and therefore, making use of heuristics makes sense. So, this is just a recap of what we did with branch and bound, that eventually it found this path to the goal node, which came from here actually. Maintains distinct paths as separate nodes in the search space, ends up expanding the same state space nodes again and again essentially. And we had said that we could do a little bit of optimization there, but then Dijkstra's algorithm gives us a much better idea, which says that you only maintain one graph, and for all the nodes that you keep exploring, you keep track of what is the best parent you came from. So, the parent pointers will tell you what is the shortest path, but it had no sense of direction essentially. It keeps only one copy of each node and adjusts the parent pointer when it finds a better path to that node. So, we saw that initially the better, when we started by expanding A or inspecting A as a child of S, we thought that S is the best path to S, and if you remember, that was a cost 6, but later we found this cheaper path which was via B, which is of cost 5. This is a feature we will adapt into A star. Both branch and bound and Dijkstra's algorithm have no sense of direction, and we had said that once you start this, then this is the closest nodes is what they will keep extending essentially. So, in this, but something like this order, it will generate the nodes, and eventually of course, it will exhaust all those nodes and find a path to the goal node essentially. To give you a sense of direction, we borrow what we did in best first search, which is to use a heuristic function which estimates the distance to the goal essentially. So, we are going to combine these three aspects, the aspects from this different algorithm. According to best first search, candidates which appear to be closest to the goal. Okay, remember that this is only an estimate, and then we choose the node with the lowest H value in the hope of finding the solution sooner. But when we combine it with the features of branch and bound, we will see that we will also find an optimal solution, and we will see the conditions under which that happens. So, as we said earlier, it only looks ahead, and it is possible that best first would have found this path to the goal, but which is not necessarily the shortest path. That is because it only looks ahead, it does not look behind. A star, as we have been saying, combines the best features of all these algorithms. So, what is the cost that we will associate with nodes? So, look at this diagram. So, we have the start node on the left, we have the goal node on the right, and we have some open list in which we have candidate nodes. So, in this example, there are 3 nodes. For all nodes, we will compute a value called f of n, that is standard terminology in A star, which will have 2 components, g of n and h of n. What are these? G of n is the actual cost of the solution found from the start node to the node n. So, supposing this is the node n that we are talking about, G of n says that this is the actual cost found to the node n. This is what branch and bound or Dijkstra's algorithm would have essentially. H of n is our good old heuristic function, which says that you estimate the distance to the goal, and essentially f of n is the sum of g of n plus h of n, and that is what we use in our search algorithm. So, this is the algorithm A star. Each candidate is tagged with the estimated cost of the complete solution. F of n is the cost of the complete solution passing through node n, where, as we have said, Gn is the known cost of the path found from start to the node n, as used in the branch and bound algorithm or Dijkstra's algorithm, and h of n is the estimated cost from the node n to the goal node, as used by the best first search algorithm. The search space, as A star explores the graph, looks as follows. Then all these are the nodes which has already explored, and you can see that every node has a back pointer like in the Dijkstra's algorithm to say which is the best parent it came from. So, for example, for them this is the best parent, and so on and so forth. For every, so you can follow the trace the path back to the source from any node essentially. And of course, we have the heuristic values of the nodes which are on open that we will include in the evaluation, which is f of n. F of n, remember, is h of n plus g of n. The algorithm is going to follow the same strategy that we have been talking about, refine the best looking partial path till the best solution is fully refined. Maintain a priority queue of nodes sorted on their f values, where f is equal to g plus h for every node. Pick the lowest f value node and check whether it is the goal. That is our good old strategy that we have been following. If it is not the goal, generate its neighbors and compute their f values, and insert the new nodes into the priority queue. As we will see, we will keep only one copy of every new node that is generated. So, for existing nodes, check whether you have found a better path like we did in the Dijkstra's algorithm. So, that is going to be the strategy of A star. This is a full algorithm. Courtesy, this version is from Bhaskaran, who is helping with this course, and he has followed this style of Dijkstra's algorithm by saying that initially every node has a value of plus infinity, which is what Dijkstra's algorithm did. So, initially whenever you generate a node, you say that it has a g value which is infinity, and then of course you revise it essentially. Like the Dijkstra's algorithm, it maintains a priority queue, as we had said, and when we initialize this, we can see that the parent of the start node is null. We compute the g value of start node is 0, because the cost g value is the cost from start node to that node, and that node itself is s. Then we compute the f value, which is g of s plus h of s. Remember that h of s is a function that is a static function which somehow estimates the distance of any node to the goal node, and we put it into this open list essentially. We initialize the closed list to empty, and while open is not empty, we do the same. So, this is very similar to the algorithms that we had studied earlier. We add n to closed after we have inspected it, and we apply the goal test function. If we have it, then we call a function called reconstruct path. So, this reconstruct path function in our case will not use the closed list. We are no longer keeping node pairs that we were keeping in best first and depth first and so on. Instead, we are keeping parent pointers, and for every node we will have a parent pointer which will be used for reconstructing the path. So, if it is not a goal node, then you look at all the neighbors m which are given to us by the move gen function, and we test whether the parent node, the value of the g value of the parent node plus the cost of that edge from n to m, if it is less than the cost of g of m that is existing. What is g of m? We have already said that for all new nodes g of m will be initialized to infinity. So, obviously, this will be less than that, but it could also be less if you had already found one path to a node and then found a better path, as we did, for example, if you remember the node A when we look at the tiny search example with Dijkstra's algorithm. So, if we have found a better path to this thing, then we update everything. We say that parent of m is n, and then we say that the cost of that node m is cost of n plus cost of k of m. This is the cost that we found was a better path, remember, in this part here. And of course, we add that to h of n to give us f of m essentially. Now, there are three different cases that A-star algorithm encounters, and most algorithms, most textbooks, they mention these three cases explicitly, but here they have been included in one long things. Case one is when this m, remember this m is each neighbor that we are talking about. If m is a neighbor, so this is a neighbor m we are talking about. If m is a new node, as mentioned here, then simply we add m to open. So, we have added m to open, we know that what its g value, we know what its h value, because h value we know for any node, and we know who is the parent of m, which is n. That is what we have done at this place here. So, this is case 1 when we are generating a new node. Case 2 is when the node was already on open, and what happened was that it had some original g value, but we found a better g value, and we have updated the better g value in these lines here, and then we can simply continue. This is what, for example, Dijkstra's algorithm does essentially. In the case of A star, there is a third case which was not there in Dijkstra's algorithm, which is that the new neighbor is already on closed essentially. So, if you think about a Dijkstra's algorithm, you will see that when Dijkstra's algorithm takes a white node and colors it black, which is the white node it picks the cheapest white node and colors it black. At that point, it has already found the best path to that black node that it has created. So, it will never find a new path to a node which is already black, or in our case which is already on closed essentially. A star, that does not happen, and we will see this as we go along, and the reason for that is because A star includes this estimate h of n, which may or may not be accurate essentially. So, it is possible that the nodes that you found path earlier, you found that path earlier, you even picked it from open, then you added it to closed, you may still find a better path to that node, and we will see examples. That is the third case which is there in A star, which was not there in Dijkstra's algorithm, and that means that the node is enclosed, and if m is enclosed, then we will need to propagate this improved cost to children of m essentially, and we will see a small example which will illustrate this. And why is that? Because we have found a better path to a node which is on closed, and the fact that it is on closed means it had been expanded, its neighbors had been added, and we had found some path to its neighbors. Now, we have found a better path to m, so that improvement must be propagated to its neighbors. How does that happen? So, there is this algorithm called propagate improvement. So, given this node m which is enclosed and which we have found a better path to, then for each neighbor x of m, which is given to us by the move gen function, if we have found that this new path, which is g of m plus the cost of going from m to x, which is the edge cost, is less than what we had stored for that node x essentially, then we revise that. So, we say okay, we have found a new path. So, parent of x must be m, g of x must be g of m plus k of mx, f of x must be g of x plus h of x, and if x also happen to be enclosed, then we recursively call the propagate improvement algorithm to do that. This is something peculiar to A star algorithm, in the sense that to nodes that you have already inspected first, you can find better costs later, and a little bit later we will see that under certain conditions we can try to be closer to Dijkstra's algorithm, where you have already found the better path, but that requires an additional condition that we will need to look at. So, we need to now study as to under what conditions does A star guarantee you an optimal path, and the reason that we need to study those conditions is because we are using a heuristic function in our computation, which is an estimate of the actual distance, unlike Dijkstra's algorithm, in which we knew exactly what was the cost of reaching to a node. Okay, so we have discussed this. If we have found a better path to x, x is on closed or it may be on open, but if it is on closed, then you recursively propagate the improvement to children of x. So, here is a small example which we illustrate this. So, we have this node n that A star is about to pick. That means that see what we have, the numbers that we have in every node are the g values. So, as you can see on the top, what we have written are the g values. We have not mentioned the h values, but let us assume that whatever the h values are, this node n is the next one to be picked from open essentially. So, the nodes on closed are the ones with solid lines and the nodes with dotted edges are the nodes which are on open, and A star always picks the cheapest node from open. So, let us say that that is n essentially. It has a g value of 55 essentially. It will generate its neighbors. So, these are the neighbors that it has, and all the three cases that we talked about will come into play here. One is this first case was when it is a new node, which means it was not on open. This is the case number 1. This is case number 2, where the node is on open, and nodes like this would be case number 3, which means they were already on closed, but we may have found a better path to that essentially. So, what happens after n expands this node 55, all its children are added to the graph essentially. So, as I said, case 1 is a new node, case 2 is a node already on open, and the other nodes are where they are already on closed essentially. What is the path to n that it has found? The path to n it has found is this one, because that is where the back pointers show that the parent of n is this node with g value 50, then it is this one and then this. But to other nodes it may have found better paths. So, after this node n is expanded, what happens? You can see that for this new node we have upgraded or assigned the g value to 62. Where did this 62 come from? That is 55 plus 7, 7 is the edge cost, and we add it to open now. For this node which had a cost of 62, which has now a cost of 62, initially it had a cost of 70, as you can see here, and this cost came from this node which had a cost of 50. Now, we have found a better path. So, we have revised the parent pointer and said that its cost is 60. The same is the situation for nodes which are already on closed. So, this node, for example, its parent was the node on the top, which is 30, but now we have found a node with 55 plus 2, which is 57. Before this it was 60. How did this 60 come? We have not mentioned the g values here or the h costs here, but this h could have been cost 30. So, 30 plus 30 would have been 60. Now, what has happened is it is 55 plus 2, which is 57. So, we have found a better path. So, we remove the parent pointer for that and then we propagate. So, this is the propagation part. This one and this one. From 70 we came down to 57, or sorry, from 60 we came down to 57. So, that improvement of 3 should be propagated, and then you find that when you are doing this propagation, you find a better path to all these nodes which were already on closed, and we have also revised their parent pointers. So, this hopefully explains what happens when a new node is expanded by A star. It may find better paths to some nodes and it may add new nodes, which is the original case, first case. Next, we will look at how A star searches the implicit graph guided by the f values and generating the nodes which it does on the fly, and we will also compare it with best first search. So, we will do that next.